x's. Now the next question is a new one. We haven't done one like this. And what it says is, for what values of x is, I'm not going to read that whole next part because it sounds like gobbledygook. So what we have to do is we have to look at the domain. The domains of these. So the domain of f, go back to your f function. F of x is equal to 1 over x minus 1. Obviously there's a domain restriction because of the variable in the denominator, and x cannot equal 1 or you get a 0 there. So the domain of f is the set of all x such that x is not equal to 1. And then the domain, let's look at, of f inverse. Remember, f inverse of x is equal to 1 over x plus 1. So what is it that x can't be there? X can't be 0. So the domain of that one is the set of all x such that x cannot equal 0. So what we're going to say is, we want to know when f inverse of f of x is equal to x, and we want to know when f of f inverse of x is equal to x. So if you go back and you look at where we worked those, I'm going to put this here. F inverse of f of x, what we had was, I'm going to rewrite this, of f of x was equal to 1 over x minus 1 and then plus 1. Remember we had that back at the start? So what can you see here? It's going to be x so long as x isn't equal to 1, right? Because if x is equal to 1, you got a 0 here and that throws the whole thing off. So this is true if and only if x is not equal to 1. Now let's look at this one. If you go back and look at when we worked that, we said f of the inverse is equal to 1 over x plus 1 minus 1. That's what we ended up happening. That's what we had. That's what we ended up getting. Notice here, that'll be equal to x, all right, unless x is 0. So x can't be 0. So f of f inverse of x is equal to x if and only if x is not equal to 0. And that's what it's asking. And this is where it gets a little bit hairy. Okay, and I realize that. All right, let's look on the back. There's a theorem here. It says the graph of a function f and the graph of its inverse, f inverse, are symmetric with respect to the line y equals x. So first off, from your library of functions, remember the line y equals x is this line right here. Okay, that's the line y equals x. So inverse functions should be like mirror images of each other across that line. Okay? So if you look at example 7, and I don't know if I'm going to be able to draw this well. It says the graph shown below is that of a one-to-one function, y equals f of x. Draw the graph of its inverse. So here's the way you do it. It's not as hard as it sounds. Let me put a couple points on. We have the point -1, 0. So we have this point on our graph. We have the point -2, -1. We have that point on our graph. And we have the point 2, 1. So 1, 2, 1. So our graph, and yours looks better, looks kind of like this. This is that graph of f of x. All right? And again, I'm going to label the points 2, 1, and then we had -1, 0, and -2, -1. So let's list those. We've got the points -2, -1, -1, 0, and the point 2, 1. Well, remember what we learned when we first started. If this is f of x, a list, to do f inverse of x, what do I have to do? I just reverse those. So you have the point -1, -2. Here you have the point 0, -1. And here you have the point 1, 2. Well, I can plot those quite easily. I've got the point -1, -2, that's this one. I have the point 0, -1, that's this one. And I have the point 1, 2. That's this one. So that graph looks kind of like that. And my drawing is not symmetrical, but it should be. If it's done correctly and you did it on lined paper, you would see that this is the mirror image right across that line, y equals x. Now, some of you, because you're spatial, are going to be able to see it better on the graph. Other people, like me, who are totally not spatial, are going to have to do what I did. List your points on your original, and then do their reverses, and then plot them. And that way you can find the inverse function. Okay? Let's look at example 8. Find the inverse f of x equals 2x plus 3. So find the inverse of that function and then find the domain and range of f and f inverse. Graph them on the same coordinate plane. All right? Now, since we know that a function that's defined, f of x, has a point xy, its inverse function has a coordinate point yx. Then the way that you do this is you take your original function and you rewrite it as y equals 2x plus 3. And then that changes by reversing the x and the y to x equals 2y plus 3. You see what I just did? I just reversed my x and my y because of the definition here. Okay? And now I'm going to solve for y. So I'm going to subtract a 3. And again, you guys, this may be hard to understand conceptually, but it certainly is not a hard thing to do. So if f of x is equal to 2x plus 3, then f inverse of x is equal to x minus 3 over 2. So you see what I did? The steps were write it with a y, reverse my x and y, and then solve for my second y. All right, so I could also say that's equal to y. That's the same thing. X minus 3 over 2. So now let's look at our domains. First off, does my f of x function have a domain restriction? No, it does not have a variable with an x under it, or a variable under it. I mean a square root with a variable under it, sorry. It also does not have a variable in the denominator. Does my inverse function have a variable in the denominator? No. Does it have a root sign with a variable under it? No. So are there any domain restrictions? No. So the domain of f is just negative infinity to infinity. All right? And we also know that the domain of f inverse is negative infinity to infinity. So how do we find the range? Well, remember, the domain of one is the range of the other. So the range of f inverse is negative infinity to infinity. The domain of this one is the range of that one. So the range of f is negative infinity to infinity. Now, if those had been numbers, you would have pulled them in. So it's all the same, actually. And now what you can do is you can go back and we can graph that. And there are multiple ways to do this. I like to always put in my line, y equals x, dotted or in a different color or whatever. I could create an xy table, which is what I'm going to do. So I've got f of x right here. And then I have f inverse of x right here. So I'm going to pick some x's. Let's try 0, negative 1, 1. We're going to try 3. Okay, so let's do this one first. F of x is 2x plus 3. So if x is 0, f of x is 3. Just plug it in. Let's finish this column first because it's easier to do it that way. All right? If x is negative 1, and I put my negative 1 in here, I get 1. If x is positive 1, I get 2 times 1 is 2 plus 3 is 5. And if x is 3, I get 9. Now let's check out f inverse. So what I have is, for f inverse, I had the equation x minus 3 over 2. So these aren't going to be quite as pretty. If I put a 0 in, I get negative 3 halves. If I put a negative 1 in, Negative 1 minus 3 is negative 4 divided by 2 is negative 2. If I put a 1 in, I get negative 1. Try it. Put a 3 in, and I get 0. So now I have a list. Let's write them as points. If I have my f of x, let's just do those. Some of its points, those are right here. I've got the points 0, 3, negative 1, 1, 1, 5, and 3, 9. And then if I list my f inverse points, here, that is this one and this one, I have the points 0, negative 3 halves. I've got the point negative 1, negative 2, 1, negative 1, and 3, 0. But I also have the reverses of these, 5, 1, and 9, 3. We know that. So you have enough points now to plot. I'm not going to do that on here because it's not going to turn out right. But you're going to see that they are mirror images across the line y equals x. Actually, I guess I better do it. So we have the point here, 0, 3, 0, 3. Let's do 1, 2, 3 like this. That's the point 0, 3. We have the point negative 1, 1, negative 1, 1. And we have the point 1, 5. 1, 5, which is up here, somewhere like this. And that line looks kind of like this. Now, its mirror image, I've got the point 0, negative 3 halves. I've got the point negative 1 minus 2. Actually, you know what? Let's just do, I think I'll do the inverses of the 3 I did on here. So let's write these. So I've got the point 0, 3. I've got the point 1, 5. And I have the point negative 1, 1. Let's just do the inverses. So let's do the point 1, negative 1. Let's do the point 3, 0. And let's do the point 5, 1. So you see, this line goes like this, and they should be symmetric around that line, y equals x. A lot of ways to approach that. All right, so look at the bottom of the notes. It says, procedures for finding the inverse of a one-to-one function. Super easy. Step 1. In y equals f of x, interchange the variables x and y to get x equals f of y. That's what we did originally in that last problem. This represents the inverse function f inverse implicitly. If possible, solve the implicit equation for y in terms of x, and that gives it to you explicitly. And then check the result by showing that f inverse of f of x equals f of f inverse of x, and they're both equal to x. Sounds very complicated. It is not. So let's look at an example that kind of puts this all together. Example 9. We have the function f of x equals 2x plus 1 over x minus 1. And we know that x cannot equal 1. It is 1-to-1. We're told it's a 1-to-1 function, so we want to find its inverse and check the result. So what are we going to do? We're going to change the f of x to y and rewrite the equation so that it looks like this. And then its inverse is x equals, so wherever there's a y, we put an x, wherever there's an x, we put a y. 2y plus 1 over y minus 1. This is called the implicit form. And now we want to solve that for y. How do we solve this for y? We use the LCD. And the LCD is y minus 1. So I'm going to multiply both sides by y minus 1. And on the left-hand side, I get x times y minus 1 equals, those cross cancel, 2y plus 1. Go ahead and distribute. xy minus x equals 2y plus 1. I'm going to add an x to both sides, and I get xy equals 2y plus x plus 1. I'm going to subtract the 2y. How do I know to do that? Because I'm trying to solve for y, so I want to get all the y's on one side. And I have xy minus 2y equals x plus 1. Now that I have all the y's on one side, I can factor out the y. X minus 2 equals x plus 1. And now all I have to do is divide by the stuff that is not y. And I get y equals x plus 1 over x minus 2. And that is its inverse. How do I prove that? And by the way, x cannot equal 2. We have to know that. Okay, this is the inverse. How do we check it to make sure? We say, does f inverse of f of x equal x? And then we say, and what is f of f inverse of x? It should also be x. So let's do this one first. F inverse of f of x means f inverse of f of x, go back to what f of x is, 2x plus 1 over x minus 1. All right? But that is equal to, what is our inverse equation? X plus 1 over x minus 2. So what we have to do is, everywhere we have an x in this equation, we take it out and we put in this, and this gets pretty ugly. So what we have is, take out the first x and put in that, and then plus 1 over, take out the second x and put in this, and then finish it. Those are complex fractions. That's a method to simplify. We're going to forget about this right now because I don't have space. I'll do that later on the page, okay? I shouldn't have written that there. So, how do we do a method 2 complex fraction? We find the LCD, and the LCD here is x minus 1. I put each term in parentheses, and I multiply by that LCD, x minus 1. And what we end up with is 2x plus 1 plus 1 times that is x minus 1. That's my numerator. Here, those cross cancel. 2x plus 1, be careful here, minus everything in parentheses. 2x minus 2. Let's simplify. In the numerator, I end up having a 3x. In the denominator, I have 2x plus 1 minus 2x plus 2. Those go away, so I have 3x over 3, which is equal to x. So that checked. Pain in the neck, but it checked. Now let's check it the other way, doing the opposite. Taking f of f inverse of x, and let's see what that is. That means f of, what's f inverse? It's what we found right here. X plus 1 over x minus 2. But what does that mean? It means go back to the f equation, which is right here. And everywhere you have an x, take it out and put in this. So you're going to have 2 times x plus 1 over x minus 2. And then plus 1 all over, there's another x, so take it out and put in this, minus 1. I know, it's very, very ugly. This again is a complex fraction. We're going to use method 2. The LCD here is x minus 2. Put each term in parentheses. I'm going to put this whole thing in a bracket there and write the x minus 2 outside of it. X minus 2, x minus 2. This is getting messy. Let's see what we have left. We have a 2 times x plus 1 plus a 1 times x minus 2. That's my numerator. Over x plus 1 And then we have minus 1 times x minus 2. Let's simplify. 2x plus 2 plus x minus 2 all over x plus 1 minus x plus 2. Alright, 2x plus x is 3x, 2 minus 2 is 0, x minus x is 0, 1 plus 2 is 3, and looky there, it checked also. Hope you got all that last part because I ran out of ink and had to change pens, but it all checks. If you simplify it, it'll be there. You may not be able to hear me speaking, but it'll be there. So there's a lot. There's a lot going on here. There's a lot of algebra you've got to be able to do. And if you're rusty on the whole complex fraction thing, you need to go back and review that. Now, what I'd like you to do is take the first function, f of x equals 2x plus 1 over x minus 1. And then take the inverse function, f inverse of x equals x plus 1 over x minus 2. And put those in your graphing calculator and look at them. They should be symmetrical about the line y equals x. I'm not about to try to draw that here, but put those in your graphing calculator and take a look. All right, finally, example 10. It says find the domain and range of the function 2x plus 1 x minus 1. Okay? So the domain, what we know is because there is a variable in the denominator, there is a domain restriction. So we know that x minus 1 cannot be 0. You solve that and you get x cannot be 1. All right? So the domain of f of x is the set of all x such that x cannot equal 1. Okay? But you know what? That also tells me that that is the range of f inverse. So if I want to know what the range of this one is, I got to know the domain of f inverse. Well, I'm not given f inverse, but I can certainly find it. So from the function f of x equals 2x plus 1 over x minus 1, I'm going to rewrite it as y equals 2x plus 1 over x minus 1. Okay? Now I'm going to interchange the x's and the y's, so that becomes x equals 2y plus 1 over y minus 1, which we already did in the last exercise in example 9, and we know that f inverse, if you solve this now for y, turned out to be y equals x plus 1 over x minus 2. So what's the domain of f inverse of x? It is the set of all x such that x cannot equal 2, right there. Because if it's 2, you got a 0. So now that I know the domain of this one, I know the range of my first one. The range of f of x is the set of all x such that x cannot equal 2. Right? That's the domain of this one. The range of this one is the domain of that one. So the range of f inverse is the set of all x such that x cannot equal 1. So they're just opposites of each other. So you really need to understand that. And if you'll look on page 419 in your textbook, you'll see a really good summary. I'm not going to recopy it here. You're very capable of reading it. For homework, you need to do problems 9 through 63 every other quad.